Hello everyone. Remember, the ultimate goal of this chapter is to define and compute definite integrals. So remember, the informal definition of a definite integral is if you have the graph of your function f of x and you are over the interval ab, we're talking about the area of the region between the graph and the interval ab. That area is a signed area in the sense that if that region is above the x-axis, then we say that this region is positive. If it's below the x-axis, then we say that this region is negative. So we want to find a way to define and compute this. If your function is nice, so if it's built with straight line or arc of circles, you can use basic geometry to compute definite integrals. But in general, very quickly, these regions, even if they're simple to visualize, are extremely difficult to compute. To get there, we're going to use the following strategy. The first step of the strategy is to first construct an approximation for that definite integral. And that approximation is going to use basic geometry. And actually here, it's going to be using just a bunch of rectangles. And covering a definite integrals with a bunch of rectangles is also known as Riemann sums. And what a coincidence, this is the name of this section. So we're going to build Riemann sums to approximate definite integrals. And this is what we're going to do in this section. And then we're going to go from approximation to the exact value to a definition to compute the exact value using, of course, one of our favorite tool, limits. And this is what we'll do in the next section. So in the next section, I will present the actual limit definition of definite integrals. And this is the definition of the definite integrals. But that's the subject for the next section. Now, I really want to stress the fact that computing Riemann sums is one of the easiest topic that you're going to study in an integral calculus course. Because in a nutshell, a Riemann sum is just computing the areas of a bunch of rectangles to approximate a definite integral. So we have a fancy region here in gray, and we're going to cover it with a bunch of rectangles. And computing the areas of those rectangles, this is a Riemann sum. So tonight, if you're having dinner with your parents, and then your mother says to you, "Child, what did you learn today?" You actually have two options. You could say A, "Mother, I've used the areas of a bunch of rectangles to cover a gray region. I'm so smart." Or B, you could say, "Mother, I've used a Riemann sum to approximate a definite integral of a function over an interval AB." So it's your choice. Are you going to go with A or B? But both of them are the exact same shit. So here's for you a very quick summary of what a Riemann sum is and to build the intuition behind the notation and terminology. So we have this gray region and we want to approximate this region with a bunch of rectangles. So the first thing you do is you take your interval AB and you break it into sub-intervals. So here we go. Boom. Okay, I have here in my picture taking the time to break my interval AB into 5 sub-intervals. So then what I typically do once I have my interval divided into sub-intervals, I just like to label the endpoints. So you start with x0, and then you just go x1, x2, x3, x4, and x5. It ends at x5 because in this case, in my picture, I have 5 sub-intervals. Now, what you could do is you could label these sub-intervals. You could call the first sub-interval I1, I for interval, 1 for the first one, and then you have I2, I3, I4, and I5. So the reason why I broke my interval AB into 5 sub-intervals is because I want to use 5 rectangles to cover that region. All those rectangles, the bases of those rectangles, will be those subintervals. So the width of the bases are going to be I1, I2, I3, I4, and I5. Well, the length of those subintervals. And basically what I want to do now is to decide how high these rectangles, these 5 rectangles are going to be. And of course, you want these rectangles to follow the function somehow. So what you do, for every subinterval, you pick a point. And then with that point that you pick, that you choose, you compute the value of that function at that point, and you use that value to set the height of those rectangles. For example, here, I'm just going to pick randomly 5 points, one in each subintervals. So for the first subinterval, I choose C1, C4, choosing 1 for the first one. So here we go. Boom. So that's my C1 here. And then once you have a value chosen between x0 and x1, you compute the output. So on top of that point, you just compute the output. So here we go. Poof. So I'm computing the output of the function at C1. So I compute f at C1, and this is going to be the height of my first rectangle. So now what I do, I just use that y value as the height of my rectangle. So it's like I'm assuming that the function is now constant, or a constant value. So same height throughout. And then what I do is I just compute f at C1 times the width of that interval. And that is going to be my first rectangle. So here we go. Boom. So that's my first rectangle. So that rectangle is roughly the first portion of my definite integral over the first subinterval I1. And then what I need to do is simply repeat the process for every subinterval I2, I3, I4, and I5. Now let's pick a point in I2, I3, I4, and I5. So, and I will call them C2, C3, C4, and C5. So here we go. Boom. Here are my points. Now for every single point, I'm going to evaluate the function at C2, C3, C4, and C5. And these are going to be the heights of my rectangles. So the second one, the third one, the fourth one, and the fifth one. So here we go. Boom. So those now are the heights of my 4 rectangles. So for the second interval, the third one, the fourth one, and the fifth one. So if you compute f of C2, then you use that value for the height of the second rectangle. Then you compute f of C3, poof, for the height of the third rectangle. Then you compute f of C4 for, poof, the height of the fifth rectangle. And then f of C5 for the height of the fifth rectangle. And now, if you just shade all the regions of those under those heights, you can visualize the areas of the second, the third, the fourth, and the fifth rectangles. So poof, here are the areas. And you can see like these 5 rectangles together, these red regions together, they're very close to the gray region. We're missing out some of the chunks, but it's a very nice approximation. So again here, I cannot stress enough the fact that Riemann sum is just teaching you how to construct rectangles to cover regions that represents definite integrals. So it's very, very nice. The notation is a bit annoying, the terminology is a bit annoying, but it's really doing something that is supposed to be intuitive. We're using rectangles to cover fancy regions. That's it, that's all, okay? All right, now let's go over the technicality of those definitions and let's do some examples together. All right, here we go. Here's the definition. And again, for Riemann sums, try to really understand what a Riemann sum is from the point of view of geometry. We are covering fancy regions with a bunch of rectangles, okay? But when you're talking about this in general, you need notation, and the notation might seem too much, but it's really there to reflect on the fact that you already understand what a Riemann sum is, and you're just trying to summarize this in general. Anyway, so let's use rectangles to approximate definite integrals. So how do you construct a Riemann sum? So the first part is you divide your interval into n sub-intervals. Typically in a question, this is specified, like use n equal 3, use n equal 5, etc. And the length of those sub-intervals are typically called delta x. And delta x is just the length of the original interval, AB, and you divide it by n, so that's why it's b minus a over n. So we have n sub-intervals, and then for those sub-intervals, we label the endpoints using xk. And the way you label the xk is by starting at the beginning, so at a, so we call x0 the first endpoint, and it starts at a, and then you just make little leaps of delta x. So x1 is just x0 plus delta x, x2 is just x0 plus 2 times delta x, and etc. all the way up to xn, which is x0 plus n times delta x, which will give you your last endpoint, b. So the xk's are just the endpoints. Maybe I'll just write that down. Endpoints of the sub-intervals. And again, here, the best way to understand this is really with an example like we just did. So the kth subinterval, we typically use the notation ik for it. So it's just the interval from x, k minus 1. So the leftmost point of that interval is xk minus 1 to xk, which is the rightmost point. Remember this because we're going to be using this in the near future. And ck is just any point. So when you're doing a Riemann sum, you just choose a point. So again, here the notation CK, C is for choosing, K is because we're in the kth subinterval. So what is a Riemann sum? The Riemann sum is just the sum of the areas of n rectangles, where the height of those rectangles are given by the value of the function at CK. So f of CK is the height of the kth rectangle, and the base of that rectangle, the width of the base, is delta x for all of them. So RK is the area of the kth rectangle, base times height. So base is delta x, height is f of ck. And then the Riemann sum is just adding all those areas from the first one, R1, plus the second one, R2, plus etc. to the last one. Since we're using n rectangles in general, the last area is labeled Rn. So we have R1 plus R2 plus R3 plus R4 plus etc. to Rn. For R1, the area is f of c1 delta x. For R2, it's f of c2 delta x, all the way up to the last one where it's f of cn delta x. So you can sum them up together. And the notation that we use for the Riemann sum using n subinterval is RIE, so for Riemann, and in bracket n. Of course, it looks like rien if you are a little bit francophone. I'm so evil. So rien n is just a Riemann sum using n rectangles. And here for notation, so when you're summing a lot of them, the only thing that changes in that sum here is the index for C, because c'est en français, for C. So we go from FC1 delta x plus FC2 delta x plus FC3 delta x all the way up to FCN delta x. So only the index, the sub-index of C is changing. So you can use the sigma notation. So we're summing n terms from the first one to the nth one. So FCK delta x. So where k goes from 1 to n. Okay, so that's just the sigma notation. Well, you don't really need the sigma notation when you're just doing a Riemann sum where n is small. So a couple of remarks here. Rien n is an approximation. So when you're covering a region with a bunch of rectangles, you're not getting the exact value. And of course, that Riemann sum depends on the choice of CK. So if you're doing a Riemann sum with n subintervals and I'm doing another one, we might not end up with the same number because we're potentially choosing different CKs because we're strong, independent people. We can choose whatever we want. But even if in general for a Riemann sum CK can be anything, in practice, I will teach you how to do specific examples of Riemann sum. In particular, we're going to look at the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum, okay, where you choose CK in a very specific fashion. So our next example is we want to illustrate Re5 for a function f of x over the interval AB, where the CKs are already specified for us. So here we go. So here, just to make it clear, here's my subdivision. So I have my 5 subinterval y5 because we're doing Re5, so a Riemann sum with 5 sub-rectangles. Sorry, yeah, with 5 rectangles. So we have 5 sub-intervals. Sorry about that. And the C's are already chosen for us. So we can see on this picture, the endpoints are already labeled from x0 to x1 to x2 to x3 to x4 to x5. And we have C1, C2, C3, C4, and C5 already specified for us. So if you have to simply illustrate the Riemann sum, so you have to basically construct the areas of the rectangle. So for C1, you just compute the output at C1, so you get f at C1. So you just do that by drawing a point that illustrates the height of that point, and then the first rectangle is just going to be using this value. So that's my R1, that's my first rectangle. So remember, the base is delta x, the width of the subinterval, and the height is f at C1. So for C2, so C2 here, we're going to use the height at C2. So we have the second height. So that's my second rectangle here. So that's R2. So f at C2 times delta x. And for my third rectangle, here we go, f at C3. I'm using f at C3 for the height of my rectangle. So here we go. So the third rectangle, f of C3 times delta x, C4. Again here, remember those are specified for us. So this would be the R4, f at C4 times delta x. And then C5, the rightmost point here. So this is going to be my height. And here we go. So that's my R5. So f at C5 times delta x is my fifth rectangle. So when you're summing up these 5 rectangles, the areas of those 5 rectangles, we get Re5. Again, here the C's are given to us. They're randomly chosen. There's not any pattern. And again, here it's really important to understand that saying that I'm computing the Riemann sum with 5 subintervals is a bit too general. You're not going to get one specific value. So the next move is to introduce some very special Riemann sum, some very specific Riemann sum, where the values for those approximations are going to be the same, no matter if I do it or if you do it, as long as we all do it correctly. So here are 3 very important Riemann sums. And when we're going to ask you to compute Riemann sums, we will ask you to compute one of the following 3 Riemann sums. So these Riemann sums are just ways of choosing the CKs. Okay, so we're telling you how to choose the CKs. Are you using the left, the right, or the midpoint sum? So what is the left sum? So here, for every subintervals, the left sum, the CK, is simply the leftmost point. So the value of CK is xk minus 1, which is a notation for the leftmost point. So if we're asking you to compute the left sum, all the CKs are the leftmost point. If we're asking you to compute the right sum, then all the CKs are going to be the rightmost points, which are denoted by xk. And what is the midpoint sum? Again, here, very intuitive stuff. Where is the midpoint of a subinterval? It's right in the middle. If you want a formula for it, you can just compute the average of the endpoint, but you go right in the middle. So these Riemann sums are very algorithmic. So if we ask you to compute the left Riemann sum, then you know that you have to divide your interval into n pieces, and then the CKs are all the left points. If you are asked to compute the right Riemann sum using n subintervals, you divide into n pieces and you choose all the right points for every subintervals. Same thing for the middle. You divide, you choose the midpoint. So let's just do some examples. Here's an example. So let f of x equal to 0.5x cubed minus x squared plus 2. And we're going to study this function over the interval minus 0.5 to 2. So let's draw and compute L5, so the left Riemann sum using 5 rectangles. Then we'll draw and compute R5, so the right Riemann sum using, again, 5 rectangles. And then we'll draw and compute Mi5, so the midpoint sum using 5 rectangles. So for all those questions, the starting point, the A value is minus 0.5, the B value is 2, the delta X, the width of every subintervals, which is also the length of the base of all those rectangles, will be 2 minus 0.5 over 5, so 0.5 long. So the width of every subintervals is 0.5, or the length of the bases of all those rectangles are going to be 0.5. The boundary point, so if you start at minus 0.5 and you jump by 0.5, x0, the beginning, is minus 0.5, then x1 is 0, then x2 is 0.5, x3 is 1, x4 is 1.5, and x5 is 2. All right, let's do the first one, L5. So here we have the function already drawn. We want the definite integral, so we want to use a Riemann sum to approximate the gray region, and we're doing this with L5. So here for us, it's already divided into 5 pieces, and what I'm going to do is just label the C1, C2, C3, C4, C5 using the left Riemann sum. So over the first subinterval between minus 0.5 and 0, C1 is going to be minus 0.5. So the leftmost point between 0 and 0.5, the leftmost point is going to be 0. So C2 is 0. Between 0.5 and 1, C3 is going to be 0.5. Between 1 and 1.5, C4 is going to be 1. Forgot my dash for C3 here. And then between 1.5 and 2, C5 is going to be 1.5. Now for all those points, you just compute the output at C1, at C2, at C3, at C4, and at C5. And those points are going to be used to be set as the height of those rectangles. So here we go. So I'm just going to draw the corresponding heights and shade the corresponding rectangle. So poof, here we go. So that's the corresponding left Riemann sum in red. Now, if you want to compute it, the computation is not too difficult. It's borderline tedious, actually. So if you want to compute L5, so here we go. So we want to compute L5. So we have to just add all those rectangles. So here we go. So it's going to be the value of the function at minus 0.5 times 0.5. So this is really just the height times the base. So the first rectangle plus the second one, f at 0 times 0.5. The third rectangle is f at 0.5 times 0.5. The fourth rectangle is f at 1 times 0.5. And the last rectangle, the height is f at 1.5 times 0.5. And if you do this, and remember, we know what f is, so it's just a question of evaluating your function at those c values. Make sure you understand that the computation, the final answer is 4.21875. So make sure, so you're just evaluating your function 5 times and you get your approximation. So the areas of those 5 rectangles together is 4.21875. Next is R5. So for R5, again, same divisions here, same x0 to x5, but now between the interval minus 0.5 and 0, the first C is going to be 0. So your C1 is 0, C2 is 0.5, C3 is 1, C4 is 1.5, and C5 is 2. So for every subinterval, you're using the rightmost point. So you compute the output at C1 for the height of the first rectangle. F of C2 will be the height of the second rectangle. F of C3, the third one. F of C4, and F of C5. And now if you draw the corresponding heights and you shade the corresponding area, poof. So here's R5. So those red regions together, they correspond to the right Riemann sum using 5 rectangles. And now if you want to compute it, so just by looking at those rectangles, so you want to compute R5. So here we go. So R5, poof. So if you want R5, so the first rectangle is F at 0 times 0.5 and etc. So here we go. So this corresponds to the area of those 5 rectangles. And if you use your calculator, remember F, we know what F is, so you just have to do 5 evaluations, sum them up, multiply by 0.5, and the final answer is 4.375. So again, make sure you know how to compute those. So verify that my computations are correct. Now for Mi5, so using the midpoint summation, Riemann sum, so between minus 0.5 and 0, C1 is going to be minus 0.25, so that's going to be my C1. Between 0 and 0.5, you're going to use 0.25, so this is going to be C2. Between 0.5 and 1, 0.75, that's going to be C3. Between 1 and 1.5, 1.25, that's going to be C4. And between 1.5 and 2, in the middle, you're going to be using 1.75, that's going to be C5. So you evaluate your function at C1, at C2, at C3, at C4, and at C5. And then you can use those points to set the height of those 5 rectangles. So here we go. Poof. So those 5 rectangles are now shaded in red. And if you want to compute them, this one is a bit annoying to compute for sure. But if you want to compute Mi5, okay, so what you do is you just poof. So Mi5 is just F at minus 0.25 times 0.5 plus F at 0.25 times 0.5, etc. And make sure you double check that the output for this approximation is 4.277344. So using your calculator. So we know what the function is. It's just a question of annoyingly computing 5 outputs. Okay, and then you get your approximation. All right, there's one more example, but I will let you try it on your own since this example is a bit simpler than this one. So Riemann sums are just computing areas of rectangles. Okay, so you're using rectangles to approximate like fancy areas. In particular, there's 3 Riemann sums that you need to be comfortable with in the sense that you need to be able to use them to approximate the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum. So for this section where we were approximating definite integrals using Riemann sums, in other words, where we were using the areas of a bunch of rectangles to approximate like a certain region, that's it. That's all. Bye-bye.